Welcome to ETHDam, to ETHDam, to ETHDam, to ETHDam, to ETHDam.
Hi, I'm Yuriko. Today I'm excited to share about what I have been recently working on, which is publicly verifiable, private, and collaborative AI training in a decentralized network. So I started my exploration with this question: what if you don't have to reveal your personal data, but you can still contribute to training a machine learning model? So for example, you can build privacy-preserving recommendation system for dApps with anonymous users. Or you can build anonymous or crowdsourced healthcare data analysis platform. Or you can even put investors' personal diary into training a machine learning model that predicts liquidity of some asset in the market. But the idea here is, what I want to do essentially is to capture the hidden trend. Data is by nature in silo and scattered, and it only becomes meaningful relative to the other. But data only gets collected and analyzed when people who have power decides to do so. So here's my question: what happens if we make ML model training more permissionless? Then I got to learn about this machine learning training method called federated learning, in which basically you can upload training process to the client side, and after clients train a local model on their own data, they upload the model updates to the server, and server can aggregate this local model updates to build the global model, and clients can fetch this global model to run inference. But traditionally, verifiability is not required in federated learning because, for example, it's used in a setting where there are two different branches in the same bank. And for example, it's really hard to export a data from Europe to the US because of GDPR. So they have to train a model in a federated way. Or two different corporations make a business alignment with each other first before the collaboration. And then they have to train a model in a federated way again. So it's not that they don't trust with each other, but it's just hard to export their data to each other, so they do federated learning. But for my setting, which is a decentralized network, for mutually distrusted parties to collaborate on training, verifiability to prove that they did something that they were supposed to do is necessary. So what does snarkify? Clients have to prove that they did a training, and also this process of masking the trained model correctly. And I will explain why you have to mask model when they publish their locally trained model. And then servers also have to prove that they did aggregation correctly. So to visually represent what I just explained, they are clients on the bottom, and they have to train the model locally on their own. And then while doing so, they generate ZK, and then they upload the mask model parameters and the ZK proof. And after this masking ZK proof verifies, server can aggregate this uploaded mask models, and then they can aggregate the global model. Sorry, they can aggregate the local models to build the global model. And then after this aggregation proof verifies, anyone can fetch this global model from blockchain. And to zoom into each part of my system, what I've built, first, local training on client side. They do multi-class classification task on iris flower data set. So given some attributes of flower, they classify which type of flower it is. And the training algorithm I used is fairly simple. It's a logistic regression circuit, which was written by another team called HashCloak for their CoNoir ML project. So I just imported this circuit. And the important point here is, again, the client's data never leaves their own device for the training. And the part of masking the model, I would say this is the only cryptographic part except for ZK in my whole system. But why do you need to mask a model in the first place? Because there are several types of attacks known, such that just by looking at weights and biases, model parameters, you can infer some information about the training data set, such as gradient inversion attacks, membership inference attacks, and so on. So in production of federated learning libraries, differential privacy is used because it's more efficient. Because the way how it works is basically you just have to add the noise to the raw data. So there's a trade-off between there's a trade-off between accuracy and privacy. So I wanted to explore more of a cryptographic way to mask the model. So I asked myself, how can clients mask model in such a way that the server can compute some of the raw models without knowing each individual values? That means that we need ETHDam homomorphism. So you would naturally think that maybe you need MPC or FHE, but it's pretty slow, especially when you have to perform a multiplication. And I wanted to perform multiplication for weighted average, so I was looking for another way. And it turned out that you just need this one-time pad technique to mask the model. So there was this paper to talk about this technique, which was published by Google for the original federated learning paper. And I guess you can call it like a type of MPC. But the important point here is that there's no decryption needed at the end, because masks that were added or subtracted at the client side will naturally cancel out with each other. And I think it's pretty interesting to see how it works, so I'm going to explain it now. So first, you have to put clients in a ring topology like this. And then clients have to generate a pairwise shared mask between each other. For example, there's a mask 1, 2 between client 1 and client 2, and there's mask 2, 3 between client 2 and client 3. And then what clients have to compute locally on their own is, given a raw model R, they have to add a pairwise shared masks that they generated with their right-hand side neighbor, and they also have to subtract the masks they generated with left-hand side neighbor. So for example, client 3's perspective, they add mask 3, 1 on the right-hand side, and then they subtract mask 2, 3 on the left-hand side. So you can see that when server aggregate sum up these mask models, M1, M2, M3, the little m's that were added or subtracted on the client side will be canceled out with each other, and then you get the sum of the raw models at the end. And if you understand this, it's pretty obvious, but the privacy on the raw models are big Rn. Each client can only calculate the masks with their own neighbors. So, for example, from client 1's perspective, they don't know mask M23. So client 1 cannot reconstruct neither raw model R2 from the client 2 or raw model R3 from the client 3. And how did I build this more concretely? I used Diffie-Hellman key exchange library, more specifically ECDH library, inside zk-kit noir library set developed by PSE. So the way it works is that each client have to publish, first they generate private key, public key pair, and then they publish public key, and then they fetch their neighbor's public key and multiply it with their own secret key. So that's how they compute the shared masks between each other. And to summarize, this is like the sequence diagram to represent how the whole system works. And just to recap, the clients first train local model on their own data, and then they generate a training proof, and they submit this training proof and their public key to the blockchain. And after training proof verifies, their public key is registered on chain. And at this point, we consider this as a sign of their participation to the collaborative training. And then we set these clients in a ring topology. And based on this ring topology, clients fetch their neighbors' public keys, and then locally computes their mask. And then using this value, they mask their own raw models, and then they submit the mask models and also masking proof to the blockchain. And after masking proof verifies, and this masked model is registered on chain, and then server can fetch the masked models from on chain for all the clients. And then server aggregates these local models and then generate an aggregation proof for the aggregation process. And then server submits the global model they aggregated and also the proof for the aggregation. And then after aggregation proof verified, then this global model that server submitted is registered on chain, and anyone, including the clients, can fetch this global model. And then they can use this for inference. I'm going to skip this for the sake of time constraint. And future research direction. So right now, the one-time path technique I just explained has a pretty weak security, because imagine if you are a client. If an attacker colludes with your two neighbors, it will reveal your raw models. So this is way worse than T out of N threshold security model of an MPC. And in terms of efficiency, you have to generate this shared mask for each model parameter. So the complexity is it's going to linearly grow with the model size. But using this thing called packed secret sharing, you can encode multiple secrets. So for example, in our case, model parameters into a single polynomial. And addition on the encrypted values won't require any interactions or communication between server and client. And we did multiplication for weighted average, but I think we can offload this to the client side, so we can skip the multiplication on top of encrypted data. And the second thing is that this construction doesn't allow any clients dropout or real-time join for the newcomers, new clients who wants to join. And this paper published by production level federated learning library called Flower says that if you increase the number of the nodes that you have to communicate with each other a little bit, which is log n, you can then the server can tolerate some clients drop out, meaning that they can reconstruct the secret value for the remaining clients for aggregation. And the real-time join thing, I haven't come up with any algorithm, so I have to think more. And for the rest of the future research, it's going to be more about the data science, intersection of data science and ZK, so I think it's a little fun to switch the gear here. But if your assumption is that you can't really trust the clients, I think it'll make sense to ask them to prove that they use the valid training data set as well. So I found this research that looking at the trained model, if the weights are weirdly skewed to some specific number, it's kind of suspicious that they didn't use a correct or valid data set. And this is some very new idea that I'm still ruminating on. But let's say we pre-train a foundational model and publish this somewhere out there, and assume that each client, Ethereum client, represents some marginalized community. They hold some data set for a marginalized community. Then what we can do is let them locally fine-tune this model on top of the foundational model, and then aggregate them to build a fair global model as a public good and leave it on Ethereum. And what we can do is to use this to mitigate algorithm bias. So let's say if a culprit uses more fair global model, then they can say that they're yeah, they're like more fair or something. But I'm still thinking, like, does it really make sense to do this in an anonymous, decentralized network? I still have to think. And then finally, it's really important to think the incentive mechanism to how to incentivize people to publish high quality data. But the definition of high quality really depends on the question of what's the objective for collaboration. So yeah, we first have to think this question and carefully design an incentive mechanism for people to submit data for collaboration. And that's it. Thank you for listening. And I put all the I published blog posts recently and then put this on my social. So let's connect if you like this kind of research. Thank you.
Yes, thank you very much, Yuriko.